Now, what happens when you add X2 to an alkene in the presence of a nucleophilic solvent? So we've gone over before how we've used non-nucleophilic solvents, but what happens if you have water, for example? Well, in this reaction, we're going to form the same bromonium ion that we've seen before, but now water is going to interact with it. We're going to bite back and attack that alkene. We're going to form our bromonium ion. And now what's going to happen is that this bromonium ion is surrounded by water. Remember that water is our solvent. And so there's a very large excess of it. That means this bromonium ion only sees water. Even though we kicked out Br minus, what this reactive intermediate sees is actually just tons and tons and tons and tons and tons of water. There's so many water molecules around that this is going to be more likely to interact with this bromonium ion because it's just all around. It's surrounding everything. So what's going to happen is we're going to do the same thing as before when we just had X2. We're going to take our nucleophile and we're going to attack one of the partially positive carbons, okay? We have two carbons here that are partially positive. The bromonium has a positive charge on that bromine atom, and it's pulling electron density away. So we're going to take one of our water molecules and attack on the underside of this leaving group. Then we're going to kick out our leaving group. Now it's still kind of attached, as you can see. So really what's going on is we end up having our bromine, and then on the other side, we've added water. Now water still has that extra proton on it, so it's positively charged there. What can happen is we're going to take another water molecule and we're just going to deprotonate it. We don't like to isolate things that are really reactive. This protonated intermediate I've drawn after that water attacks has a really highly acidic proton. And when we're trying to isolate organic compounds, we don't typically isolate those. All right. So we're going to deprotonate that to form our desired Halohydrin product is what it's called. I just said a new word, so let me write this down. Halohydrin. I think it's an older term for essentially having some kind of a halide here and then an OH group and then whatever else you want on your compound, okay? These are just R's. But essentially the key here is that this halohydrin is this OH group, and anti to it is a halogen, okay? Now, what we formed here also can form an enantiomer. So this is racemic. And we know this because we can have the water attack on either side of our bromonium ion. So here's our bromonium ion here. So our bromonium ion is that three-membered bromine carbon-carbon ring that looks really odd. Huge leaving group, and it's sitting on either side, and it's going to block one of the sides when we do the attack. And again, this reaction also makes this anti-product. The OH group and bromine are anti to each other. OH and Br are anti. This also works really well with chlorine. These are the two most synthetically useful variants of this X2 addition in water. Before we get to a practice problem, let's look at this addition of an alkene with a very strong acid. And we've seen this before with HBr, for example. The alkene adds this hydrogen and it kicks out Br minus. And what we see is that we end up forming a full-on carbocation. Now, this carbocation is actually flat, right? And it can add either above or below. So I'm going to redraw this just a little bit with wedges and dashes to showcase and really highlight this trigonal planar nature of this carbocation. Now, this empty p orbital can be attacked by a nucleophile either above or below, right? So if we have a nucleophile, we can either attack here or we can attack here. This leads to that anti or syn addition, essentially, where this second addition here can be above or below. So we could get anti or syn products here. Or another way to think about it is that that center is going to be racemized. Whatever's going on at that center, it's going to be, if it forms a chiral center, it will be RS. We form a full carbocation. Now, what about the addition of an alkene to Br2? Well, let's walk through this again. So we have our alkene. We're going to attack the Br, kick out our leaving group, and this is going to bite back to form that bromonium ion. I'm going to draw this a little differently than I did before, and I'm going to put the bromine here in line with the piece of paper. So this is our bromonium ion. And it's stable because every atom here has a full octet. Because one of the sides is blocked and we don't have a full-on carbocation like we did in the top here, when we have a nucleophile, it's only going to add on the bottom side, all right? So the approach is from the bottom. So this will attack opposite. So it attacks opposite to the leaving group here because the leaving group is just blocking one of the sides. In this case, it's the top, all right? So this is only going to give us this anti product where we have the two groups anti to each other. Whereas if we had a full carbocation, so in this case on the top here, we have a carbocation. Remember that we can attack the top or the bottom of that full-on carbocation. Now, I didn't finish my arrow to the nucleophile attacking one of these carbons that are partially positive. We have a positive charge on our bromine ion here. We've got those two lone pairs. Now, both of these carbons are partially positive on this bromonium ion. And I'd love for you to pause the video and ask yourself which one of these is going to be most likely to be attacked by nucleophile. So essentially you're asking which one of those two carbons is most partially positive. The one on the left is the most partially positive. And we could think about this kind of like our carbocation studies. If we look at this bromonium ion, the one side that's most substituted would be the one on the left. And you can kind of, this is how I view it. I think about it like this. Now, we know that this doesn't form, but you could kind of think about that if I were to kick out this bromine leaving group, that would put a full-on carbocation here. Now that can form on the left, right? But if I had tried to kick it out the other way, I would have that primary carbocation, which is really not good. But this one is good. And so it's because of that, the carbon here on the left that's the most substituted is most likely to get attacked by a nucleophile. So we're going to attack this carbon and then we're going to kick this open. And this is where we end up getting that anti-configuration. But more importantly, now we have regioselectivity involved here. Which side of this bromonium ion is going to be attacked is dependent upon how substituted it is. So the more substituted side gets attacked by nucleophiles. Let's just write that down. So when we think about regioselectivity, and remember, regioselectivity is just what region of the molecule chemistry is happening at. And if it's regioselective, it means certain regions are more likely to do chemistry. That's how I think about it, at least. So for the regioselectivity here, we have the most substituted side of bromonium is attacked. By nucleophile. All right, by a nucleophile. So that's kind of the second piece of information about these bromonium ions. Not only do they fully block one of the sides and gives you this antiproduct, they don't form the carbocation, but two, one of those two carbons, if they differ in substitution, will be favored for that second nucleophilic attack. Let's do a practice problem together where we go over exactly that. So let's look at this problem here, X2 addition in water. So we have Br2 and we have water, all right? We know we have an alkene. We're going to make that bromonium ion. So let's do that first. So I'm going to attack the bromine here with my alkene, kick out Br minus, bite back with that bromine to form our bromonium ion. Now, I draw the bromine coming forward. You can draw it going backwards, depends on if you like to draw wedges or dashes on your pieces of paper. It might be worthwhile for you to go through a practice problem where you also push them both back and see if you get the same products. You will get the same racemic mixture that I'm showing, but useful to think about. All right, so we have our methyl there. Now I put my methyl back. Right? So wherever you're adding the bromine, you need to put that methyl opposite of it, okay? And so now let's look at what we have. We have Br minus. And what else do we have in solution? We have water, right? We know that water is in a large excess. We have tons of it around. So we're going to take our water here and we're going to look at, now we have lots of waters around. Now on a mechanism, you don't have to draw all of them. You just draw one. I'm just highlighting here that there's tons of them. Now, which of the two sides of our bromonium ion are we going to attack? The most substituted side. All right, so the most substituted side is attacked, and that's because that's more partially positive. So we're going to attack this and we're going to end up forming, we've got our water that attacked opposite, so it will be coming down. We still have that extra proton there. Here's our methyl group. Our methyl group was pushed forward, right? It's water's attacking from below and pushing everything up and out, okay? So water and bromine need to be opposite. And that methyl, you just make sure that you get the methyl out of the way of the water is how I like to think about it. So the water attacked from the bottom. So bottom attack, bottom side attack, whatever you want to say here. But it's attacking opposite of our leaving group, which is here the bromine. So the bromine and water are opposite. And so now what we're going to do is we're just going to take water and deprotonate. Take off that proton from the water we just added. And here's our product. OH, methyl, and our bromine. Now this is racemic. We can form both of the enantiomers here. We could have had the bromine down, all right? Now the OH group is still going to attack on the same side. It's going to attack on the side where that methyl is at because it's most substituted on that side. But we will have a racemic product, and then here's our product here from this reaction. So in this video, we also talked about Br addition with nucleophilic solvents. And we also looked at this regioselectivity of where this nucleophilic solvent will add. All right, that's it for this video, and I will see you in the next video.